Hello friends, welcome to my channel. Let's have a look at problem 449, Serialize and Deserialize binary search tree. In this video, we're going to share a solution based on post-order traversal. And this is the first video for this problem. And in a follow-up video, we're going to share a solution based on preorder traversal. First, let's look at the problem statement. So in this problem, we are required to design an algorithm to serialize and deserialize a binary search tree. So there's no restriction on how our serialization and deserialization algorithm should work. We need to ensure that a binary search tree can be serialized to a string, and this string can be deserialized to the original tree structure. So the encoded string should be as compact as possible. So here are two examples. Actually, example 2 is a special case which corresponds to a null tree. And example 1 is a binary search tree with 3 nodes. So this is still not very representative in some sense. So the constraints for this problem are the following. First, the number of nodes in the tree is in the range given by the closed interval 0 and 10 to the power 4. 0 corresponds to a null tree, for example, in example 2. So actually we need to pay some attention to this edge case. Secondly, the node value is in between 0 and 10 to the power 4. And lastly, the input tree is guaranteed to be a binary search tree. So with that said, we are ready to look at the analysis and the coding. First, we are going to use post-order traversal in this video. So this is the first video for this problem. In this video, actually our purpose on one hand is to solve this problem itself, and on the other hand, we would like to practice the post-order traversal of binary search tree, or in general binary tree. So here we are going to write in both recursion format and iterative format. So before we do the analysis, let's first recall. In-order traversal of binary search tree yields increasing list, right? So this is good if we want to find a increasing list from a binary search tree. However, it's difficult, if not impossible, to convert to the original binary search tree from the in-order traversal result, right? So this is the one fact we need to notice. So however, actually we can recover binary search tree from either the post-order traversal result or pre-order traversal result. Both will do. So in this first video, we're going to use post-order traversal to do serialization and deserialization. So the idea actually is very simple. So assume that the post-order traversal of a binary search tree is given like this: 3, 2, 4, 10, 9, 7, and 5. So we separate use comma. Actually, we can use the star or something else. So we know that we are doing post-order traversal. So the last bit number 5 actually corresponds to the root of the original whole binary tree, a binary search tree. And then by binary search property, we know that if we compare with 5, so 3, 2, 4, so this subarray corresponds to the left subtree, right, which is also a binary search tree, right? So in other words, we need to build the left binary search tree out of 3, 2, 4. So similarly, 10, 9, 7, because they are all larger than 5, they correspond to the right subtree. So with that clear, so actually the building process can be easily done by a recursion, right? So with the analysis covered, now let's look at the coding. So the coding actually is very straightforward. So for the serialization, so we can do a post-order traversal, and then we can make it a string, right? So let's first write a post-order traversal. Post-order. So we can accept a tree node. So for this, actually, we can write in one line, but no, let's split that. So first, if not root. So in this case, so we are going to return an empty list. So this is the one case. In other case, so we can regard this as also a stop condition for this, or base case for this traversal recursion format of post-order traversal. So we are going to return the post-order traversal result of root left, and then we concatenate with the post-order traversal of root right. And then because we are doing post-order traversal, so we're going to add the corresponding result for the root value at the end, right? So this simple function gives us the post-order traversal result of the root or binary search tree. So then what we are going to do is to do the serialization. So we are going to use this star. Let's see, John. So I'm going to map all the elements in the return and by the to be a string. So I'm apply this function to post-order traversal of this root, right? So this is the serialization part. So we call this one, and then we do a map using string, and then we join, right? So this returns us a string according to the problem requirement. So next we do the decoding. So for this, this data will be a serialization. So let's first transform this data to be a list of integers. So data to be so here, because we are using this serialization, so we're going to do split, right? So what we're going to do is that, so we're going to do this integer x for x in data. So we're going to split around this star, right? So here actually we can add a filter. So if x, so in order to consider the empty case, so it's not absolutely necessary, but we need to keep in mind the empty tree case, right? So this is the data. This data now actually is a list of integers corresponding to the post-order traversal number list, right? So we want to reconstruct the original binary search tree out of this data. So now we can write a hyperfunction. So let's call it hyperfunction builder, right? Build. So we're going to build out of this data, right? So we can let's see, we do not need to use this data as a argument. Let's see, we have a lower bound, so that is float. So let's see, negative infinity, and we have an upper bound, so this is a float, positive infinity. So this function signature is similar as what we did when we check if a binary tree is a binary search tree, right? So here what we are going to do, first let's look at the base case. If not data, or data -1 is less than the lower bound, or data -1 is larger than the upper bound. In this case, we are going to return, right? We return nothing. So next, what we are going to do is that, so first we are going to pop the last data out of this list, right? So that data corresponds to the root. So let's do this. Root equals tree node. So value will be, let me do this, which will be more clear. So let's see, data pop. So let's call the value equals the value, right? Then what we're going to do is that, so we're going to, so this pop operation is very important for us. So next, what we're going to do is we're going to do root right. So root right, because we are doing post order from left, right, and root value. The first pop actually corresponds to the root value of the whole tree. And then if we continue to do pop, so this pop, we're going to pop from here, and the value corresponds to the root of the right subtree, right? So we do right first. And this we're going to do as build. So this is a self-call. So the lower bound will be the value itself. The reason is that so we'll consider the right subtree. It's going to be larger than the root value. So then the upper bound is still the previous upper bound. So now we are going to build the left subtree. It's going to build. So then the lower bound is still the previous lower bound, and the upper bound will be value now. So as we connect the root with the right subtree and left subtree, notice the order here. We first do right and then do left due to the pop order, right? And then we're going to return root. So this is the hyperfunction. So after we do this, actually we just need to return build, right? So we actually use some keywords arguments. So the default will be float, infinity, negative infinity, and positive infinity. So up to now, I guess we are ready to do a check. So yeah, it passes example 1. Now let's look at example 2 for the empty case. So this case, and this is the general logic. In some formats of solutions, we need to, if for safety, we can do a special treatment. But now this should work. Yeah, it passes the second example. So now let's look at the generic case. Yeah, it passes all the generic cases. So this way, actually, up to now, we found a full solution to this problem. However, what we want to do is to practice post-order traversal, and then we want to write another format. So this is a recursion format. So I'm going to write a solution for the traversal using iterative format. So this is also very important to understand or master. So for this, we're going to do post-order traversal, right? So I'm going to first initialize a result as empty, right? So if not root, so I'm going to return this result, right? Otherwise, so we're going to initialize a stack. So let's call it S, contains the root. And then what we're going to do is, well, S. So what we're going to do is that we get the current node S pop, right? Then we're going to append the result to node value. And then what we're going to do so is to check the left node. So node left, right? If node left, so we're going to append node left. And if node right, so we're going to do S append node right. So notice that this order is very important. So we first do check left, then check right. And then afterwards, what we're going to do is to do a reverse. So this actually corresponds to the post-order traversal in this format. So now let me change this one to be V1. And then let's, so here, because I call post-order, then we call this function, right? And then let's check if it works. Yeah, it passes this one. Let's do a generic check. Yeah, it passes all the cases. So with that said, basically we finished our practice. So here our purpose, direct purpose, is solving this problem. And also we want to practice the post-order traversal algorithm for binary tree, or here binary search tree. So here the first version of post-order traversal is in recursive format, and here this post-order traversal is in iterative format. So both the two formats are actually good to master. So for us, So the latter actually is related to, for example, the iterative format of preorder traversal or in-order traversal. You can try for that, or you can check the corresponding videos in my channel. So with that said, I guess that's it for this video. So in a follow-up video, we're going to share solutions for this problem using preorder traversal. So you're welcome to check the corresponding video out. With that said, I guess that's it. Thank you.